All right, we're looking over this problem here where there are two masses and they are connected by a rope, and the rope is not going to stretch, right? It's just sitting there, and there's an applied force to the right. It's a frictionless surface, so it shouldn't be too bad, right?
Right.
All right, so it asks first for a clearly labeled free body diagram for M1. So I put M1 right here, and I put a dot in the middle of it, and you tell me what other things are happening to M1.
We got gravity, we got mg.
Mg which way?
Down.
Down. So I put a little mg right here.
We got the normal force.
Okay, because it's on a surface and the surface is saying you can't go through me, and how big is that normal force?
Equivalent to mg.
Okay, and when you're doing that, you're actually saying Newton's second law, right? You're saying there is no acceleration in the y direction. And so we've got the net force equals 0, the upward force equals the downward force. Great. There's something else acting on M1.
Tension.
Tension, which way?
To the right.
Tension to the right. And we don't know how big tension is, and so I'm just going to label it as a capital T. That's our free body diagram for M1. We're done. So some people wanted to put leftward forces on M1. That could have been explained by a friction situation, but we don't have friction here.
So why are we not putting like vector hats on like?
That was sloppy. Well done, Kurt.
Okay.
We totally need vector hats on all this stuff in here. That points out. Yeah, cool. I ought to put vector hats on all my vectors when I'm being careful. Thank you. Okay, so next it asks us, because this problem kind of works us through the ultimate goal. The ultimate goal, if I'll flip to the next page, is to find out the acceleration and the tension force. So we're asked for those two things that are kind of the obvious unknowns in this situation right here. We're working towards that goal, so we need to make another free body diagram. Naturally, that is the thing to do, right? Aren't free body diagrams bread and butter for you?
Yeah.
Yeah, okay. So M2 is a little bit bigger. I'm going to emphasize that in the free body diagram for M2. Here's M2. I have a dot in the middle of it. What do we do?
You have same thing like mg and fn.
Okay, but now I notice that it's a separate m, so I draw this a little bit longer, and I'm going to call it M2 times baby g. Good, that's M1 times baby g, and then there's another force Fn, right?
Yep.
But also bigger, correspondingly the same size as M2 baby g. This is the normal force for the other box. What else is going on with mass 2?
Tension.
I'm going to remind you of this picture right here. Tension. Which way does tension pull M2?
To the left.
Tension pulls M2 to the left. Is it fair for us to identify this tension as the same as the rightward tension on M1?
Yeah.
Yes.
Why?
Because it's the same string.
Same string. And the string doesn't have mass, so it's sort of like a third law pair in itself. The string is pulling to the left and pulling to the right the same.
Yeah.
Okay? So the other important thing is we're going to get to situations in which tension is not the same for a given string if the string is doing something else in the middle. Like it's rotating something, then it could be more complicated. If there's spring, oh my gosh, absolutely. We will, yeah. Whew. So let's not talk about any of that stuff. We have a very simple situation here in which the string is massless, not doing anything, so the tension is the same between the two. Good. Do we have all the forces labeled for M2?
No. Force applied.
There's this big elephant in the room, the applied force, and it's probably bigger than the tension because my impression is that this system will be accelerating to the right. Is that your impression as well, Elizabeth?
Yes.
Okay, super. So I'm going to just call this the applied force, though, and I'm going to put a vector hat on top of it so Kurt's not disappointed in me again. Now, it says use Newton's second law to write an equation for the tension in the string based on your free body diagram for M1. Based on this, can we write an equation for tension? Using Newton's second law. Let's just start by writing down Newton's second law for this situation here. It says Newton's second law is the net force. Now, I'm interested in the x direction, so I'm going to write net force in the x direction is mass times acceleration in the x direction. Good?
Mm-hmm. Yeah.
Okay, I don't need vector hats on this, Kurt. Why?
Because it's an equation and we're going to find out the...
No.
Because we know where it's pointing.
We know that we're already talking about the x direction. Yeah, so it's not a vector equation which would involve x, y, and possibly z, but this is just for x. So we're going to designate positive and negative x with minus signs if we need to. Okay, so then what?
Put in what the force applied.
Awesome.
Or what, add them up.
Yeah, add up all the forces, right? This says add up all the forces in x. Golly, there's just one, right? And so I say, is that not the applied force, because this is for M1. I put it over here on this right side. So this is M1. I should note that in the mass, right? And then the net force in the x direction is just what on M1?
Tension.
Okay, so I'm going to say, oh, is it positive or negative?
Positive.
Got to be careful, right? So the tension is M1 times the acceleration in the x direction. I'm just going to leave off the x subscript because I acknowledge there's no acceleration in the y direction. Cool. I'm gonna put a box around this because this meets our goal of an equation for tension based on Newton's second law. Then we go over here and we say, we can use Newton's second law on this box also. We could say the net force in the x direction is m2 times the acceleration. But look, this is the acceleration of box 2. And this is the acceleration of box 1, but they're attached with a dang string that doesn't stretch. How do the accelerations relate?
It's gonna be the same.
It's gonna be the same. The boxes are tied together. You might also have a situation in which two boxes are pushed and they're smashed into each other, like I'm pushing that direction. In that case also, the accelerations for the two boxes would be the same. All right? So having the two accelerations the same and having the two tensions the same gives us a lot of strength. Because I'm feeling like that kind of two equations, two unknowns kind of fun, right? You feeling that? Morgan has silently nodded. She is feeling that. But I'm not sure I'm convinced. You really are feeling that, right?
Yeah.
All right. So how do I deal with this? It says add them up. What does it do?
You have the tension and the applied force, and you add them up.
Uh-huh. But do I say tension plus applied force?
No, it's a,
applied force minus tension.
Why?
Because
they're going in opposite direction.
yeah, and applied force is to the right, which is positive.
Okay.
And then tension is to the left, which is negative.
Love it. So I'm going to write applied force minus tension equals m2 times acceleration. I'm going to put a box around this as well. These are the two equations that I created, and I got them from Newton's second law. Every time a question asks you about force or acceleration, you should make a free body diagram for everything involved. Then you should write down Newton's second law, and then you should solve those equations. Plug in what Newton's second law is telling you. Now, it says, it goes one step farther in this particular problem further, and it says, what is an equation for tension? So that makes me feel like they want us to solve this for tension, so I'll just do that in purple. Tension then is F applied minus M2A. Is that true? Did I make a mistake with my algebra? Joey's checked it, and it is true. Now, the next question, this is step 5, it says find the acceleration of the system by simultaneously setting up and solving the system of two equations. First, you have to recognize we have a system of two equations. Look at this. Two equations, this one, and two unknowns, acceleration and tension. Cool? Because we're given M1, and we're given M2, and we're given the applied force. So, what does that mean to set them up and solve them?
Plug in the number.
Not yet.
I've done
Solve 1 for A.
Cool, we could do that, and then we would have A equals T over M1. Then I'd plug it into this equation, and guess what would be left in this equation? No A. But it says, let's get an equation for A, so that might not be the most elegant way to do that.
Wait, are we on 5?
Yeah.
Substitute T.
Yeah.
T is T. The nice thing about having two equations that are already dang solved for T is we can say the right side is equal to the right side because the left side is equal to the left side. There's like transitivity or something, isn't there? X is Y and Y is X, and Z is X and Y is Z and something. Yeah, right. Okay, so I remember that vaguely. This is M2A and this is M1A. Look at that. Isn't that nice? So a lot of people who aren't listening to me blab are wondering how the heck I got that equation. Well, you'll just have to rewind and listen to me blab, right? What are we trying to find, A?
Yeah.
Yeah.
It's an algebra problem now, right?
Yeah.
What do you do?
I would add M to the other side.
Add N.
M mass 2
Math 1.
times acceleration.
You're talking about this term here, you would add that to both sides?
Yeah.
I think that's a fine idea. I'll do that as well. I get F applied equals M1A plus M2A. When you're looking at an equation like that, that feels like it could be solved. It feels like we're on the home front now, right? What do?
Factor out the A.
Factor! When I factor, I always think about putting an A over here and putting parentheses in there and like inverse distributing.
So
Like,
it would be M1 plus M2.
wouldn't it then?
times A.
Because if I had M1 plus M2 here, I could distribute A and I would get M1A plus M2A. So yeah, absolutely.
Divide
You would,
M1 and M2.
yeah, you can just add up M1 and M2 and then divide it out.
And this is a very interesting conclusion. We're finding that the acceleration of the system, remember it's the acceleration of one block and it's the acceleration of the other block, their collective acceleration is going to be how much force you applied on the whole system divided by this,
That makes sense.
the mass
That's what
of
I
the
would
whole
get wrong.
system.
Yeah.
So some people were able to get to this acceleration without doing this long process that led to it. But this acceleration right here, maybe it makes a ton of sense. Maybe this is just Newton's second law as it applies to the entire system. right?
That's why I messed up. That's what. Yeah. Okay.
It's good, huh? It's good. Now, how are we going to find the magnitude of the tension in the string?
Well, once you have acceleration, you already know the mass of the block, so you can just plug that in.
Yeah.
Want tension. Okay, you said I have acceleration, agreed. And what equation we're going to use for tension? Because I have two equations for tension over here. I've got this one and this one. Which one do you like?
I like that one.
Which one? I can't tell which one you
The
mean.
one, your left. No, your right.
That one.
My left.
Internet people, this is your right, I hope. Are you on your head while you're watching this? Oh my goodness. This is great because it's direct. We're just going to multiply the acceleration by one of the numbers, right?
Yeah.
So, by the way, tension then, in this case we were given some numbers, and the tension is going to be that acceleration. You guys want to throw a number on this acceleration? Do you have that?
1.
It's 1.0 meters per second squared. So we're just going to be multiplying that acceleration by mass 1. That's what our equation says for tension right there. And mass 1 was, wait for it, 0.8 kilograms. So tension is 0.8 kilograms times 1 meter per second squared. If you multiply those, you get 0.8 newtons. Okay, cool. But you're doubting me. Thomas is looking at me out of the corner of his eye. He's not so sure about any of this nonsense. Fine, Thomas. Do it this way. Go. Thomas doesn't have a calculator. Thomas, what are we gonna do? Get him a calculator. Thomas, I need you to find the tension. Because the applied force is 2.2 newtons, and then you need to do some other stuff with M2. Do you remember what M2 is?
Like 1.4.
1.4. Okay, go. Thomas plugs in the applied force to his calculator. It says 2.2, right? And then what? What do you do next? He puts the minus sign into his calculator.
Yes.
Check. Now what?
M2A.
M2 times A. What's M2?
1.4.
Awesome. And he multiplies that by 1, which is his favorite calculation. Did you actually multiply it by 1?
Yes.
He multiplied it by 1, internet people, he did! What did he get?
0.8.
Shut up! That's what we got when we got it the other way.
Mind blown.
Okay, all right, let's go on then. What else did they want? Did they want anything else?
They wanted
How fast?
how fast it was going.
Those are stupid questions. Let's not do them. And that could have been explained by a friction situation, but we don't have friction here, so.
So why are we not putting like vector hats on like?
That was sloppy. Well done,
Okay, I've
Kurt.
okay.
We totally need vector hats on
That's
all this stuff in here.
confusing me
That points down. Yeah, cool. I ought to put vector hats on all my vectors when I'm being careful. Thank you. Okay, so we've got the net force equals 0. The upward force equals the downward force. Great. There's something else acting on M1.
Tension.
Tension, which way?
To the
To the
right.
right.
Tension to the right. And we don't know how big tension is, and so I'm just going to label it as a capital T. That's our free body diagram for M1. We're done. So some people wanted to put leftward forces on M1. What other things are happening to M1?
We got gravity. We got mg.
MG which way?
Down.
Down. So
We
I
got
put a little MG right
We
here.
got the normal force.
Normal
up.
force.
Okay, because it's on a surface, and the surface is saying you can't go through me, and how big is that normal force?
Equivalent to
Same.
mg.
Okay, and when you're doing that, you're actually saying Newton's second law, right? You're saying there is no acceleration in the y direction. Next it asks us, because this problem kind of works us through the ultimate goal. The ultimate goal, if I'll flip to the next page, is to find out the acceleration and the tension force. So we're asked for those two things that are kind of the obvious unknowns in this situation right here. We're working towards that goal, so we need to make another free body diagram. Naturally, that is the thing to do. All right, we're looking over this problem here where there are two masses and they are connected by a rope, and the rope is not going to stretch, right? It's just sitting there, and there's an applied force to the right. It's a frictionless surface, so it shouldn't be too bad, right?
Right.
All right,
Yeah.
so it asks first for a clearly labeled free body diagram for M1. So I put M1 right here, and I put a dot in the middle of it, and you tell me